Is my camera? It's in the upstairs. Okay. Put it in. Why is this not working?
We have 3 midterms in this class, right?
Yes. Let's see, maybe this won't work in the zoomed in level. Let's see. So it's only Curtis, you? Yeah, Curtis, I did get your email about the scanning. I will do that probably today itself and send it to you. So that should be easy.
All right, sounds good.
Yeah. So we have a homework 9. This should be new. Is this visible for a few minutes? Maybe it will get better. Curtis?
I can't see you right now.
Oh, I see, I see. Yeah. That's not readable at all, right? So when is this? 19, I think. Monday. And oh, I still haven't updated this. Midterm 3. Wouldn't use that evening.
Yeah, November 6th. Yes. Yeah, Friday.
Okay. We are doing how to work with materials, even when in addition to the charges that we typically have. And this is our equations for electrostatics. Maxwell's equations, if you want. You can say this is macroscopic electrostatics. That means to say that at a microscopic level, we have charges in a material, but on a macroscopic level, they all average out, and it is just the dipole moment of that contributes. And we said it is the polarization vector. So our Maxwell's equation now is del dotted with epsilon naught E. That's equal to the charge itself. That's how the charge works. This is the charge density, if you want. So charge density contributes to the electric field. But we said if we have a material that is an additional piece to the charge density, and that's given in terms of the divergence of what we call the electric polarization of the material. So this will be the electric polarization of the material. And that's it. Like charge and density is an external quantity that's provided to us. Similarly, the electric polarization has to be provided to us. We still have del cross E is equal to 0. That stays the same. That equation doesn't change. So idea is that if we have our polarization for a material, do the divergence of that, that gives you an effective charge, add on to this, and then do the problem as if it was exactly the same. And we will use this opportunity to do some of the problems that we did not go through in detail earlier, presuming that you are familiar with that in some undergraduate courses, so we can do those integrations here. So let's take the very simple scenario where, so example, we have a planar slab. Or a polarized slab, right? That's kind of planar and slab probably are the same. Polarized slab. We can have it of finite width, but let's make a simple scenario where we have z less than 0 on the left hand side and z greater than 0. And this whole thing is a material. That whole is a material that fills half of space. That's an idealization. But remember, all these idealization works if this length is very small compared to the standard characteristic length of the material and the system, then it's as well infinite. So, and we would like to think of this as charges here. So at each point here, so this is a negative, positive, negative, positive, negative, positive. These are all aligned in a sense, and so on. So that whole material is filled in that sense. These are negative and positive charges. Each point has a dipole moment associated with it. But notice that these can also be thought of as neutral, so they kind of cancel each other. So one can imagine this to be on an average 0. So what is the electric polarization of this material? So we'll say this is having a permanent polarization. All these are aligned very well. You don't need an electric field to align it. So that's the polarization of this would be, it's along the z-axis already, so that's the direction of the polarization, right? That's z hat. Magnitude of the polarization, how much it is polarized, that's P naught. And sorry, the magnitude is, we don't need a vector. And I have to clarify that this is actually true only for z less than 0. So for that, I will say this is the Heaviside step function. So only when z is greater than 0, right? So Heaviside step function, remember, is equal to 1 if x is greater than 0, and is 0 when x is less than 0. That's a step function that survives only when x is greater than 0, but I want it to survive when x is less than 0, so that means I have to change the sign here. So I would say this is minus z. So you can say whenever 0 is greater than z. That's another way of looking at it. If this point 0 is greater than z, then, oh, did I say that's correct? 0 is greater than 0, then it's 0. So yeah, that's okay. That's your polarization. And we would like to, and let's say we also say that charge, there is no free charges. That's equal to 0. Right? So one has to distinguish between free charges and the polarization. Polarization are those charges that contribute to the dipole moment. So of course those are also charges, but we have already accounted for that in here, so we don't account for that in here. So this is equal to so that's a purely permanent polarized. Right? So we can also say this is permanently polarized slab. So permanent in the sense this is already aligned. You don't need an electric field, external electric field to polarize. So, okay, so that's good. So let's immediately find the effective charge density, which is minus of the divergence of the polarization. And once we have that, from that point on, we just pretend as if it's a charge distribution. So this is equal to minus gradient operator, which is basically the divergence when you take the dot product. And this is the hat times P naught times minus z. This has to act on all this. In general, this vector could be dependent on the coordinates. For example, if it was a sphere, it could depend, and we will later do an example where this will contribute. But at this point, this is not dependent on coordinates. Z hat is the same everywhere. This is a constant, and this is the only quantity that depends on the coordinates. So this can be written as, so this acts only on this. So this is minus P naught times Z hat dotted with gradient operator acting on minus Z. Right. Z hat dotted with the gradient operator is nothing but minus P naught times d by dz of minus Z. Right. And that we know how to do. What is the derivative of a delta function? Of a step function? At the boundary, at just where it is switching, it is not 0. In fact, it is infinity, and one can show that this is actually a delta function. But now there is a negative sign in there, so that accounts for this negative sign in here. So you get a positive P naught times delta function, where we have used the idea that derivative with respect to Heaviside step function is actually a delta function. from this point on, it's just a charge density. So what are we talking about now? So we have instead of doing the polarized slab, we just have to do a delta function slab where there is a positively charged. This is P naught. And it's clear what will be the units of P naught now? Charge per unit area, because this has to be charged per unit volume, and this is 1 over length. So this has to be charged per unit area. So P naught should have those units in there. And this is a problem that we can do independently. Remember, this is a plate, right? It's not a line. We have a plate, and the electric field will be having some quantity on the right. And we also expect electric field to go this way, right? If electric field from this contribution alone will be on both sides. So let's calculate this P naught. So let's say change the, or calculate this electric field due to this contribution. Now I have to work on this a little. Oh no, it's not. No. Curtis, just let me know once I reach the bottom of the zoomed area. I'm not able to zoom out today. So when I reach the bottom of that zoomed area, let me know so that I can change the camera. Okay, so our equation becomes dotted with epsilon naught E is equal to P naught times delta function. And that's your effective rho effective. We know how to calculate the electric field or the electric potential to begin with. So electric potential, let me write that. The electric field is equal to the negative gradient of the electric potential, and the electric potential using superposition principle is 1 over 4 pi epsilon naught times d cubed r prime. So integrate all over the places where there are charges, and this is rho effective now. This is always applicable. Right? That's our Coulomb's law, if you want. It's equal to substitute our charge density. So that's minus infinity to plus infinity dx prime, dy prime, and that is dz prime. Now that's P naught delta of z, right? It's just z prime now. It's divided by the distance in rectangular coordinates is x minus x prime. Remember, x, y, z is your observation point. But remembering, so this is the observer, and this is the source. Like the source is coming from the charge density. And this is equal to square root of x minus x prime square, y minus y prime square, plus z minus z prime square. So the electric field is given in terms of the potential. Potential is calculated using this integral. We of course know the electric field due to a plate, but we are actually evaluating the electric potential associated with that. By the way, what is the electric field due to a charged plate, infinitely charged, a charged plate of infinite extent?
Does not depend on distance, right?
It does not depend on the distance. It's correct. It's constant, yes, and it is dependent only on the charge density on it, which is in this case P naught. Right. So the electric field is a constant. It's in the z direction, so that's equal to z hat, and it turns out it is like this is, in this case it is P naught over 2 epsilon naught. The factor of 2 is not very obvious. Why should that factor of 2 be there? Especially if you don't know which units you're working in. So we'll check that out. But what will be the electric potential for this contribution?
Would it be proportional to the rate?
It's proportional to the z, right? Because derivative of something has to give you a constant. It has to be proportional to z, and in fact, it is negative z, right? Because if you keep a positive charge next to the plate, it should run away. Right? If you were to plot this, so this is phi, and that's r. So this should be something like this, right? Because typically, potential diagrams really work like valleys. So if you put a positive charge here, it should slide down, right? It should go to, that makes sense. But we will see that there's a caveat, right? There could be a constant there, right? Plus a constant, what is that constant? Right? We would like to see that. And it will turn out that that's not a trivial constant. So let's do this. So this should show up what that is. Okay, so this should be reasonably clear intuitively, but let's see how this goes through. So this integral delta function is immediate. Replace z prime with 0, right? So that's p naught as a constant that comes out 4 pi epsilon naught, and we have x prime, phi prime, and z prime integral gets done. So that's x minus x prime square plus y minus y prime square plus z square. Notice that I can substitute x minus x prime to be something, y minus y prime to be something, and then I can do this integral. But let's be a little, that is, so yeah, that one I can actually do. So x prime minus x, let me call that x double prime. And y prime minus y, let's call that y double prime. In that case, dx prime is the same as dx double prime, and dy prime is the same as dy double prime. And the limits do not change. Right? And you will notice, and I do that. Oh, am I still indivisible? Yes.
Yeah, you probably have one more line.
Naught. So this is minus infinity to plus infinity dx prime, minus infinity to plus infinity dy prime, and this is x prime square plus y prime square plus z square. Notice that it seems like it does not depend on the observation point x and y, which is clear when you have a plate. So when you have an infinite plate, it doesn't matter whether you're here or here, right? As you move, it does not matter. That's that fact showing. So it is translationally awesome.
No, it doesn't really matter. Should these be double primes?
Oh, yes, double prime there. And then I can switch it back to X prime if you want. Yeah, so, but that's less confusing. After a little practice, you tend to do that, but let me be consistent here. Yeah, so thank you. Yeah. Okay, so that's an integral we have to do. Let me, before I proceed, move down the camera. Yeah. Okay. This is so we are talking about an infinite plane with x prime, y prime. It is good to go to polar coordinates immediately. So let's say x prime square plus y double prime square is equal to rho square, right? Cylindrical coordinates, and in that case, your dx prime, dy double prime is basically rho times d rho times d phi, where phi is the angle that contributes to that. So this is the same as E naught 4 pi epsilon naught times, now go from, instead of going from minus infinity to plus infinity, you go from 0 to infinity for rho, and you go from 0 to 2 pi for d phi, or phi. And it turns out that this is actually phi independent. So this is rho square plus z square. Is that clear? So instead of integrating on in rectangular coordinates, you can do polar coordinates, and if it has no angular dependence, that angular dependence will come out immediately. So this is 2 pi now. There is no phi dependence, so that phi integral can be done. Basically, move this to the right. That phi integral is just 2 pi. Right? Any questions on that? So that's equal to, so now P naught over, also there's 2 pi times, this is 2 pi times P naught divided by 4 pi epsilon naught. So you see that structure 1 over 2 epsilon naught showing up here, but remember that's the electric field, right? So we have more work to do. This is 0 to infinity rho d rho times 1 over rho square over z square. Is that an easy integral to do? Probably. Okay. Okay. So. Okay. So we have the electric potential to be given as P naught over 2 epsilon naught. I cancel the 2 pi and 4 pi. And this is 0 to infinity rho d rho over rho square plus z square. Right? An immediate substitution would be rho squared plus z squared is equal to t squared. Yeah. Right. Then 2 times rho d rho is equal to 2 times t dt. Right. And that gives you, so that's equal to P naught over 2 epsilon naught. And this is 0 to infinity. The rho d rho is the same as t dt. That's t times dt divided by this is t squared. And we see the problem immediately. T and t cancels out. It's p naught over 2 epsilon naught 0 to infinity of dt. Right, that goes to infinity. Right? That diverges immediately. So that's not very convenient because we would like to actually differentiate this with respect to, take the gradient of this with respect to the position and to actually get the electric field. So what happens? So one might argue that, oh, infinity doesn't matter, but if infinity doesn't matter, if it's a constant, then the derivative of that is actually 0. Right? So let's go back, right? So let's go back a little. We want to capture this structure of this infinity. How does this grow, right? So questions? Yeah. So we want to capture some structure in this so that we can actually take the differentiation. So we have to do something. So one process could be that this is p naught over 2 epsilon naught, and this is limit. Let's say that you don't go all the way because this seems to be our cause of the problem, right? Infinite is down here. You're stretching all the way in the material. So let's limit the radius of this row. So this is 0 to some large radius r, right? And I want to take the limit of r tends to infinity. Right? This is basically saying that you have a plate which is constructed in the following way. So that's your radius r. In the limit r tends to infinity, this is actually an infinite plate, right? That should be the same, right? So this is rho d rho over rho squared. Now, while we are doing this is one of the first problems you see where we are trying to give some meaning to the infinity that you get. Notice this is an artificial construction, and whatever you get, this result should be independent of this construction, right? Whether you take it as a radius, you take it as a square, or any, that would be 100 ways of constructing this plate as a limit, and it should be independent of that construction. And that is a challenge usually, that if you're in an unknown territory here, the physics actually guides you a lot. So we know what you get. So this is very convincing that when you get the answer, this is correct. But in an unknown place, it is not very clear as to just because you took it as a limit of something is actually a right answer that you get. So it has to be independent of that construction. And that's a hard thing to show that you have millions of constructions possible. Got to make it independent of. Typically, what you do is you do it in 5 different ways, and if you're getting the same answer, it's promising that you're on the right approach. If you're not getting 2 different answers using 2 different methods. So that's one note there. And let's do this integral again, right? Now we do again the same substitution. Everything works the same way. So this is 2 epsilon naught. Limit r tends to infinity. And pretty much the same substitution, just that this time, when you, did we actually do that correct here? When rho was equal to 0, t is z, right? T is z. So probably you could have seen that construction in there, right? So it's t is z. And in that manner, you probably can even see the structure of infinity better. So this is z, and then you see that, this is p naught over 2 epsilon naught. In a crude way, this is infinity minus z, right? And that minus z sort of gives you your answer, right? You guys pointed out that, your potential should be negative z, that's your negative z. But there's an infinity sitting there. That's not convenient. So you do see that answer right there, but that's an infinity. So let's see some structure of that. So we see that in the terms of r, right? So this is r. This is your, do the same thing, right? So this is now not r. So when I put this r here, so it is z squared plus r squared, I guess. And it's the square root of that. Okay, and this is z, right? Magnitude of z. So, so z on one end if you want. So this is t dt again, those cancellations happen, and we have dt. So we get this, and we do this again, E naught over 2 epsilon naught, limit r tends to infinity of, do the same thing, right? So this is z squared plus r squared minus magnitude of z. Now the key in here is that we have to actually take the limit, right? R has to go to infinity. So, but now we know how that goes. When R is very large, Z can be neglected. So this is R minus Z. Not still, you don't escape this whole thing. So this is, maybe you can write it this way. This is R, right? This is minus Z. It's just that this is actually an infinite quantity, except that now you know how it grows. Right? It is infinity, but you can think of it as if you have it, like typically in real, in a physical universe, this length cannot go beyond the size of the universe, right? That's the best. In that sense, this is a finite quantity, but that's a physical argument. Once you have that, once you accept that, so this is with that caveat of that infinite quantity, and also remember that electric potential, can this be measured? So that's another quantity, another thing you can talk about. Like
You have to take the 2 points, right?
2 points. It's always the difference, correct? It's always a change in electric potential that you. So another argument could be that when you do that change in potential, this quantity goes away, right? So this usually doesn't contribute to your measurements. So this is called a gauge in that sense. In magnetostatics, this will become much more pronounced as a whole gauge transformation that we can do and not disturb the system at all, or Maxwell's equation at all. So this is the simplest way. This is just a constant. Later on, we will see that it's a whole derivative or something that we can. So in that sense, you can again try to satisfy that. Okay, that might be okay. But those are the issues that stay, linger on, and it gets more and more murky as we proceed. It doesn't go away in the strict sense. Okay, with those comments, let me do the electric field, right? So electric field is negative gradient of the electric potential, which is equal to the negative. Oh, I'm still. Yes, almost. That's P naught over 2 epsilon naught. This depends only on Z, so it is d by dz. And there's a negative here and a negative there, so this becomes a positive. And this is a constant. This doesn't depend on Z. So let's see. What is the derivative of a magnitude of a function? So notice if you were to plot Z for greater than 0, this is Z. For less than 0, actually, it is this way. Right? Straight line would be this way, but it is upward or downward. So its derivative will be +1 on the right side, -1 on the left hand side. Oh, what happened to my vector? So that should be a vector. Right? Z hat depends on Z hat. So that's equal to plus z hat P naught over 2 epsilon naught. If this was charge density or charge per unit area, so that's charge per unit area over 2 epsilon naught, and this is for z greater than 0, and for z less than 0, it is minus z hat P naught over 2 epsilon naught. That's okay. So that seems like that's an electric field for a charged plate, but it might be confusing as to what does z less than 0 mean, right? Remember, we have a material out there with dominant polarization. What's the electric field quantity doing there? So let's go back and look at this. Any questions at this stage? This is from to a certain extent, this is the electric potential and electric field due to a charged plate, right? Which we see long ago. But now we want to combine this with the material properties that we discussed, okay? Which is a small extension to this. But this should be clear. Questions? Okay, so let me go back and maybe so. Oops. Yeah, this should be fine. So we have, remember, L dotted with epsilon E is equal to rho, which is 0 basically, minus L dotted with P. Correct. This is 0. No more problem. P, we said, is equal to z hat d naught theta of minus z, right? Which means that P is in the z direction, so this is your P. That's your P. And it's 0 on the right hand side. That's your P. Like this is equal to 0. Is that clear what I mean? Like less than this, you have this vector. On the right hand side, there is no contribution. We said that the divergence of P is equal to rho effective, which is equal to P naught times delta function. But then that creates an electric field if you calculate it. So electric field now is this way, right? So that's your electric field. That's your electric field, like on both right and left. But this equation can be written as divergence of epsilon naught E plus P is equal to 0. And we said inside a material, we don't talk about electric field, we talk about the displacement vector. So this equation, Maxwell's equation, should be read off as the divergence of the displacement vector is equal to charge, which is of course 0 in our case, where D is equal to epsilon E plus P. And where is my P over 2? Where did this go? maybe it is. Okay, so if I get this correct, I'll check my notes. This is the same, so notice that this is P naught, correct? So here it is P naught on the right, and sorry, this is 0 here, and P naught in here. Down there, let's do epsilon naught, right? If I multiply with epsilon naught, I get a P naught over 2 on this side, and P naught 2 in the opposite direction on the left. So I get on the right hand side, it's very clear that this is the electric field that I expect. So that's P naught over 2. So that's your D, right? So let me say this is D is equal to P naught over 2 times 2 over 2 times Z hat. And on the left hand side, I have to subtract these two things. P naught on the right, there's a minus P naught, so this actually reduces to this. So this is D is equal to P naught over 2 Z hat. This, let me check. Yeah, it is actually. We had everywhere actually. Yeah. Yeah, D. Yeah, there is a there is a contribution to D. Yeah. So yeah, I think that's. Yeah, the way. Yeah, I think the interpretation in here is that. So take this permanent polarization here. Right? So this is your positive charges here, right? Which is being thought of as negative charge, negative charge, negative charge, and so on. But you can actually balance out this negative charge completely all the way to the back and say this is neutral, and somewhere at infinity, especially if this was a half slab, right? If this was a finite slab, then you would think that this is actually a negative charges in here, and that creates an electric field that goes this way, right? I don't know, I'm confused. Okay, I'll give you the interpretation later. Okay, interpret this. I'm a little confused. Interpret this. Right. Why is it in the right? Physically, do you guys have an interpretation from?
Yeah, so it should be minus P0 over 2 right, from the electric field. That's on the P, and then you plus the P, which on the left side is P0. So you get positive P0.
Positive P naught. That's correct.
So
Yeah.
I see how you get P on the left side.
Yeah, that's a mathematics. But I was saying physically, inside a material, D is. I almost expected it to be 0. Like if it is a perfect conductor. Yeah. But let's leave that. Let me not bring in my bias there.
So it's like you're saying it's like with a perfect conductor, if you apply electric field, the interior electric field exactly cancels.
Exactly.
Right?
Exactly.
And you're just like trying to apply that.
Yeah, but I think there is a slight difference there in the sense that that is an induced mechanism. This is a permanent. So that's I think now I get it. I'm getting confused here that this is a permanent polarized material. Like it's like a magnet, right? A magnet is permanently polarized magnet there. It does not depend on whether I apply an electric field or not. So this is permanently polarized. It has an electric field of itself, but then it is a material dependent electric field. So that gets contribution from the positive charge that's at the end, if you want to think of it as an imagine, if you want to imagine it like that, because that's just a construction, right? In here, what is that? Looking at this as all these getting cancelled out, that's just a construction. But overall, this is the physical parameter that you talk about for a material, and that's equal to, so now let me not do this. I think it's clear. Yeah. So this is equal to this plus this polarization. That's what decides the property of the field inside the material. Polarization plus the electric field. Later on, what I was confused about is that this could depend on the electric field, but that's not the case here. That's the case of a conductor, for example, where this depends on the electric field. That's not the case. This is just not so. So that's a material, that's an electric field generated if you go by, so that remember is a model, but this is the final structure that you want to keep. So, so yeah, extra credit, right? We needed that extra credit. So along this line of thought. I need to move the camera, I suppose. That's my remote. So, extra credit is for this was a semi-infinite play. Yes. Oh. Thank you. Extra credit is draw these lines without doing the actual calculation for a finite slab. So this is negative, positive, negative, positive. Like I think this is your part of your homework also. Right. Try to get these field lines for a finite slab. Okay, so I'll stop. I did not expect to go long.
I think in the book,